All right, starting off on example number 3, my notes say that we left off after practice problem number 2. Is that correct? Yes. Excellent. Example number 3, scientists have established that atmospheric pressure in sea level, or at sea level, is 14.7 pound per square inch, and the pressure is reduced by half for each 3.6 miles, sorry for the typo, above sea level. This rule for atmospheric pressure holds for altitudes up to 50 miles above sea level. Find the altitude above sea level at which the atmospheric pressure is 4 pounds per square inch. Okay, so we're going to use the same equation. At sea level, it is 14.7 pounds per square inch, and it is reduced by half for each 3.6 miles above sea level. In my equation, I used h instead of t since we're dealing with rising height above sea level. We're going to plug everything in. 14.7 times 1 minus 0.5 raised to the h over 3.6 power. This is because it halves every 3.6. I put days. Sorry. .6 miles. So then we get this. Take a look at the next step here. Do you guys all feel like you could figure out where this equals 4? Yes. Thank you for catching that. There we go. All right. Please solve for h when this equals 4. Here, I'll even set up the equation for you. There you go. Sorry that the copy machine is printing these little things here. And I'm going to double check and make sure I didn't accidentally use 2.6 in my answer. So I'll solve this along with you guys. Hold on 1 sec. Okay, can I see again? Yes, yes. Yes, miles. Yes. Sure. You guys close? Oh, what'd you get? Everyone else has answered. Yep. Go ahead and grab one. Great job. All right, everyone got it. You guys are awesome. Here's the answer. Are there any questions? Okay. All right. Practice problem number 3 says determine the atmospheric pressure outside an aircraft flying at 52,800 feet, which is 10 miles above sea level. Do you guys feel like you can do that? Okay. Go ahead and solve. When you have your answer, hold up your board. This time you're plugging stuff in and solving for P. Oh, and I did it again. I put 2.6. Okay. Everyone hold off on answering while I fix it. Oh, yeah. Oh, give me. It should be 4.3, I think. Hold on. 4.3. I'll give it to you. I'll check my work too, just in case. Yeah, I'm getting a 4 after the 3. All right, does anyone else have an answer? Yes. Anyone else have an answer? Should be 4.3. I think you just switched. 3, you guys have an answer? Oh, That's it. Okay. Yeah. Perfect. All right, everyone got it? Here is the answer. Are there any questions? All right, so for example number 4, we're going to make a regression model. Does anyone need a little bit more time on this page? Okay, no worries. For those of you who are done copying, go ahead and go to the next page. 1990 is 0. Go ahead and make a regression model on your calculator. Also, please notice the very last one would be 122, not 130. It counts by tens, and then for just one, it doesn't. I don't know why.
Kiwi.
Yes. So graph it and then find the regression model. Was everyone able to graph it? Okay. So please note that it is an exponential regression, which is this one. I'm getting a different model than the one they got in the book for some reason. Hold on. I'm trying to figure out if I did it wrong or if they did it wrong. You got what I got? Okay, then it must be an incorrect thing in the book. Yes. That's what I got to. Yeah. All right, so teams 2 and 4, got it? Anyone else? Actually, you know what? The answer's on the screen. I'll just give everyone a point. Just make sure that you get that. Yes. It's not getting that? Okay. Let me see. Is it possible you Oh, so it's something actually like with All right, was everyone able to get it? Okay, so go ahead and plug in, and again, I have to redo this one because the model that was in the book was incorrect. I recommend that when you're plugging something in, keep all your decimal places and then round us on the very last step. Sorry, hold on, I don't know the answer yet. Okay, can I see what you guys got? Oh, that's not what I got. Did you guys use this or did you use the rounded one? Okay, then yours is probably right. Yes. Mm-hmm. All right, so teams 2 and 4 got it. Great job. I'm asking for what is P of 122. Yes. So you use the rounded version. All right, everyone got it? Okay, So this is actually something I talked to Mr. Peluso about, just because the AP Calc exam has been around a lot longer than the AP Pre-Cal exam. So generally, if there's something we're unsure about in the AP Pre-Cal exam, we just go by whatever they've been doing in the AP Calc exam. So if you have an FRQ that says find a model for this set of data, and then for Part B or Part C it says use the model you found in Part A to calculate this or that, do they want you to use the rounded model that you found in Part A, or do they want you to use the unrounded model with as many decimal places as you can? And Mr. Peluso says he doesn't really know. So our best guess is that they're not going to mark you down for being more accurate. So my recommendation is if you get that, use all the decimal places your calculator can come up with, round at the very last step. However, I have seen a lot of answer keys for the AP exams where they'll say they'll accept this answer or this answer. And I think it's in situations like this where they say use the model you found in Part A, which you guys did, and the model you found in Part A was rounded, right? So to me, I feel like that would be a correct answer. That's our best guess. So my recommendation, when in doubt, be more accurate. As accurate as you can be. But on my tests, I'm willing to take it if you use the rounded model. That's totally fine. Are there any questions on this one? Do you feel like you guys can do practice problem 4? No, use here. Go ahead and cross out Phoenix. Continue to use 1990 as t equals 0. So this will be 50, 60, 70, and so on. And I'm going to recalculate this one too, just to make sure. Okay, this looks right. We're good. Yes. Either way is fine. I put my answer in both thousand and million. Hold on. I think you're right. I miswrote something. Hold on. Okay, can you show me one more time? I apologize. Yes, that's right. Yes, that's right. I'm pretty sure it's right. Yep, all right, everyone got it? Here is the answer. Any questions on this one? All right, logistic models. All right, I feel like we've made a few regression models today. Would you guys be okay if we just went over this? Regression models, I think you guys all feel pretty comfortable with them. They take a long time to type in all the values. So I'm assuming you guys are able to do that. This problem, everything's the same. The only difference is we're now using a logistic model, which is right here. I don't know if it's the same place for a regular TI-84, but you'd have to scroll down for it. And if you do this, you get this for Florida, and you get this for Pennsylvania. And I used F and P for Florida and Pennsylvania. One of the big differences between logistic functions and exponential functions is that logistic functions have a limit. The limit is going to be the numerator, whatever the numerator is. So the limit for Florida is 27.3504, and the limit for Pennsylvania is 13.0436. Is everyone okay so far? Yes.
How does it determine the limit? Do you have to put that in?
It's the top number. Oh, it's a regression model, so it will tell you. Here, this is if we had made a logistic regression model of the data we just used. So as you can see, C would be your numerator. And then when you graph it, it looks similar, except at the end it's approaching a limit. All right. Not yet. Sorry. All right, we ready or not yet? Not yet, okay. Can I see your packet for a second? The next section, I put it in a different order. So definitions, examples, and then I'll stop this. All right, here is the answer to the question. So it says interpret their significance. Pennsylvania had rapid growth in the first half of the 20th century and is now approaching its limit to growth. Florida is currently experiencing rapid growth but is expected to approach its limit by the end of the 21st century, according to the models. Yeah. It reflects the information. The models, you guys already know by now that models are not perfect. The more data you have, the more accurate of a model you can create. This is the model's best prediction based on very limited information. Yeah.
Why do they have limits? Like, what makes it?
Well, when dealing with population, usually population is not going to continue growing exponentially forever. At some point, it's going to start to taper off because this is the space that we have. These are the resources that we have. At some point, it's no longer going to pass some limit. So mathematically, this is a prediction of where that limit is based on a certain trend. That may or may not be the limit that Pennsylvania or Florida has. I mean, maybe they'll expand. Maybe they'll create more jobs. Maybe things will change. We don't really know. This is just based on where the trend is, where if it's starting to taper off, it's estimating where they think it's going to top off. So exponential models are nice when you have something that's going to grow exponentially forever. Logistic models are better if there's a limit to growth. All right, we're just going to do the exit ticket at our desk, if that's all right. It says use the table and an exponential regression to test the model for the population of Bulgaria. Tell you what, here's the model. You guys can all make regression models. So the question is an exponential regression model appropriate? Explain why or why not. This explain thing is going to be a thing on the exam. And generally, they're always going to have a rubric where they're looking for specific things in your explanation, and we don't know what those things are. So probably in this case, what they'd be looking for is, first of all, yes or no, and then a mathematical explanation. Preferably something that uses information you're able to glean from the data to explain whether or not you said yes or no. So in this case, give me yes or no. I'll give you 1 point for if it's the correct yes or no, and then I'll give you another point for a good explanation. And then I'll give you a sample explanation that would be a solid one to put on an exam. That's 1 point, but what's the why?
Oh.
Good explanation. Good explanation. Good explanation. The term goes on forever. On the exam, you would probably want to, it maybe increases exponentially without limit, whereas population typically has a limit. Yeah. So you would want to be a little more specific. You're right. It's increasing, and then it kind of at the end, it experiences some decline in the last few decades, right? So you would want to say a little bit more like that. All right, good answers, you guys. Here is another way you could say this. The regression model does not fit the data. Although many populations grow exponentially, we can see that bulk area has experienced several decades of decline. You could also say that populations tend to grow exponentially initially, or for a brief period of time, temporarily. In my case, I decided to use the fact that the numbers actually go down a little bit at the end. Okay, so while you guys are finishing copying this, 5B, I changed the order in your guys' packets. It starts with the definitions and examples in your packets, right? And then the proofs come later. Okay. Last year I did the proofs first, and it was a little confusing, so I changed it up. Yay, proofs, yes. Proofs are fun, and this class we get to do paragraph proofs instead of 2-column proofs. Alright, does anyone need more time? I see some people writing. I'll wait. Alright, while people are finishing, logarithms. Do you guys remember the rules of logs? Do you guys remember that have you had any exposure to logs? You guys have seen the word log in a math problem. Okay. Alright, do you guys understand that logarithmic functions and exponential functions are inverses of each other? Okay, so graphically and also algebraically, they kind of go hand in hand. Proofs also, they go hand in hand. Anyone need a little bit more time? Okay, we're going into 5B now. And I believe your note starts with this. So this is like the basic definition of logarithms. This is how you convert between logarithms and exponential functions. So if you have y equals log base b of x, then b to the y power equals x. So this raised to this power equals this. And same thing here. Remember, natural log is just log base e, so e to the y would equal x. So using those definitions, here are the basic properties of logs when you have a log base b. And here, you guys all know that if there's no base, what is the base if there's no base written? 10. A common log, that's the one that has no base, it's just going to be 10. So in your calculator, if you hit the log button, it's automatically going to be 10. Yes, you did. So we're going to do more with it. I want to remind everyone how to use logs first. Do you guys all remember, did you learn how to do logs in your calculator? Okay, so just a reminder, if you hit math, log is A, and then you can type in the base and the number. I'm going to move this over. So these are natural logs. This is log base E. at example number 1. Do you guys feel like you could solve those? A and B? Okay. Anyone need a little bit more time with this page? Okay. All right, please solve A and B. When you have your answers, please hold up your board. So what is that? I'll give it to you. But you know what you can find what those numbers are, okay? Oh, I have to solve it. It's fine.
I don't know what we're doing, but okay.
That's the first one. Can you solve the second one? Yes. Yes.
Wait, that's 32.
Yeah, you guys are about to get it. Good job. All right. Here's number 1. Are there any questions on example number 1? Okay, if you were kind of struggling with example number 1, really try practice problem number 1. It's the same procedure. You're using the same rule. See if you can figure this one out. Go ahead and do practice problem number 1. When you have your answers, hold up your board. And if you're really do both. If you're really having trouble, let me know. Yes. Or ask someone on your team. Just make sure you're understanding it. That's the first one. Good job. Yes.
We got it. We figured it out. It's a lot of parts.
You guys doing okay? Sure? Okay.
Thank you.
Okay, would anyone like me to go over how to do this? Is there anyone who would benefit from that? You guys all got that one really fast. Yeah. Would anyone like me to go over how? I don't mind. Okay. All right, let's go on to example number 2. It says, ladies, describe how to transform the graph of natural log or common log into the graph of the given function, and then sketch each graph. Okay, so what I've done here, I've graphed this one in pink and this one in blue. I'm adding 2 inside the function, so I'm going to translate 2 units to the left. It looks something like that. Here's a question. The exponential function. Where is the asymptote on the exponential function? Bonus point. If you could raise your hand and tell me, where is the asymptote? Yes.
There's a vertical asymptote.
There's no vertical
Wait, no,
asymptote.
a horizontal asymptote at 0.
At 0. Yes. So there's a horizontal asymptote at y equals 0. Awesome. I'll give another bonus point if someone can tell me the y-intercept of the exponential function. So great job. Yes.
One.
Amazing. Yes. How did you know? Yes, it intersects the y-axis at 1. So the logarithmic function, being an inverse of this, looks like this. Bonus point if someone can raise their hand and tell me, where is the vertical asymptote on this? 0. And another bonus point if someone here wants to, where does it hit the x-axis? 1. So when you're graphing things by hand, it's generally a good idea to make sure the asymptotes and the intercepts are in the correct place. The rest of the graph, especially if you're graphing it by hand, if it's a little bit off, it's okay. But asymptotes and intercepts, you're going to want to make sure those are accurate. All right, because of time, I'm just going to finish this off. So part B, this one, it's a little bit easier to see the translation if you write it like this. So what I did here is I pulled out a negative. So now I have negative, parentheses, x minus 3. So now I can see it's being reflected about the y-axis and then translated 3 units to the right. So it looks something like that. All right, and we'll pick up on practice problem number 2 next time we meet. Let me freeze it here.